Okay, so now let's start. So let's first take a look at example. Example 6.1. DC level in Y Gaussian in Y noise. So if we observe xn equal to A plus W, where W is the Y noise with variance sigma square, then the problem is to estimate A. But notice that in this case, it's more general because we can apply this to an unspecified PDF. In other words, it doesn't say Gaussian noise. No, it doesn't say that. So it does not require you to have a Gaussian noise. As long as it's white noise, that'll be good enough. We don't need it to be Gaussian. So then the problem is to estimate A. Since Wn is not necessarily Gaussian, the noise samples may be statistically dependent, even though they are uncorrelated. Okay, this sentence sounds like sounds like uh, a little bit strange, but let me explain this. If you have a Gaussian noise will be completely described by its first moment and second moment, which is the mean and variance. Okay, so if you have a Gaussian noise and then it's uncorrelated, they will not be dependent because first moment and second moment completely describes the Gaussian noise. But if it's not Gaussian, then theoretically you need infinite number of moments to be able to describe the PDF. And therefore, there is a possibility that non-Gaussian random variables are uncorrelated, but yet they are dependent because there are higher moments. The higher moments may not be zero. So they may be dependent in some way, but the second moment can be zero. Okay, so that's the explanation for this sentence. Otherwise, you may feel this is strange. How come random variables can be uncorrelated and yet dependent? That is possible for non-Gaussian. Okay, but because expect of E xn equal to A, we have from 6.4 that Sn is equal to 1 and therefore S is equal to 1. From 6.5, the BLUE is this, and 6.5, let's see, 6.5, okay, 6.5. So you plug in S equal to 1. And this is kind of a bold-face one, right? Bold-face one meaning it's a 1, 1, 1, 1 column vector with all ones in its elements. So A hat is equal to this 1 transpose multiplied by 1 over sigma square identity and then X divided by 1 transpose 1 over sigma square and identity 1 equal to 1 over n summation xn. How come? How come? Because you have one extra 1 here, right? So you have this, a lot of things cancel out, and yet there's this 1 remains, 1 over n remains in this term, and then x summation equal to x bar, and has minimum variance from 6.6. 6.6. Okay. So if this is 6.6, we have variance A hat equal to this divided by 1 transpose 1 over sigma square 1. Okay, so then we just multiply it out. The numerator, no, the denominator has a 1 over sigma square. So you take it to the numerator, you get sigma square as the numerator. 1 transpose 1 is equal to n. Okay, if you have a row vector multiplied by a column vector, then this 1 multiplied by 1 plus 1 multiplied by 1, so on and so forth, you get as a denominator. Okay, so the sample mean is the BLUE independent of the PDF of the data. Okay, so that will be the BLUE, in fact, for arbitrary PDF. Then of course it will be the NVU for Gaussian noise, because we did it before. So DC level, let's take another look. We have a DC level in uncorrelated noise. Now let Wn to be zero mean uncorrelated noise with variance this equal to sigma n squared, and repeat example 6.1 as before, s equal to 1, right? This s equal to 1 is because you have a DC level. DC level is what? DC level is just 1. It's just A. So you put 1 into this S, then you get A plus noise. Okay. So we have this A and S all formulated out. We put it into 6.5 and 6.6, which we did many times. So A hat is equal to this, variance A is equal to that. And the covariance matrix, as we said, is uncorrelated with sigma square. Okay, so you have sigma 0 square, sigma 1 square, all the way to sigma n minus 1. So all the way to sigma n minus 1. And you have 0, you have this 0 at the off diagonal noise, at the off diagonal element. And then you take the inverse. The inverse is c minus 1 equal to this and 0. Okay, I think this is trivial, right? Linear algebra. Okay, so you have A hat of what? You put this into here, you put this into here, so you get A hat and variance A hat. So you get this and this. The BLUE weights those samples most heavily with smallest variance. Let's take a look. You have a denominator here. But for xn to be in the estimator, what happens is it has to be divided by sigma n squared, right? So imagine that if sigma n is smaller, it's weighted more, right? I hope that you get the point. Sigma n is, for example, 0.001. Then when you put it at a denominator, it's going to be a large number. If sigma n is a large number like 100, you put it in the denominator, it's going to divide the value of x out, right? So this sample is kind of been weighted differently by sigma n, and it will be weighted most heavily with smaller variance. in an attempt to equalize the noise. So this is all sometimes called noise equalization. Okay, if you recall, maybe some of the things that you learn in signal processing, communications, we have equalizer. Some of the equalizer is doing this noise equalization. So, but by the time you do that, you may not be aware what happens. But at this point, I guess it's very clear we are doing optimal estimator. We are doing design for optimal estimator. And this approach of weighting the samples are actually giving us optimal weighting for the samples. If you take another perspective, when a sample is corresponding to large noise, what that means is the noise is large, so that sample is not reliable, right? It's not reliable because its noise is large. But if it corresponds to a smaller noise, then it's more reliable. Therefore, we have to weight it differently. So conceptually, that makes sense, right? That makes sense. Okay, so the denominator is a scale factor needed to make the estimator unbiased. Okay. In general, the presence of C-1 in the BLUE acts to pre-whiten. In previous chapters, we talk about whitening filter. We talk about whitening process. So if we kind of see this C minus in front of X, this is whitening, right? Whitening, we call that. So C is to pre-whiten the data prior to averaging. This was previously encountered in chapter 4, okay, in the color noise example. So it's kind of double confirmation again in this chapter to see that all of the theories are systematic and also consistent, right? Things that we talked about in previous chapter, when talked about again in this chapter, they are consistent. We don't have contradictions. Okay, so also in the example that the identical estimator for A was obtained because the Gaussian noise assumption, the estimator could be said to be efficient and hence NVU, right? It's Gaussian, then it will be NVU. Okay, it's not just coincidental that the NVU for Gaussian and the BLUE are identical. This is a general result that says that for estimation of the parameter, a linear model, the BLUE is identical to NVU for Gaussian noise. Okay, so we will talk more about this in 6.5. Okay. Okay, so as we always do, we first do scalar version and then we do a vector version. So if the parameter to be estimated is a p by 1 vector parameter, then the for estimator in the to be linear in the data we have to rewrite. It's in the vector form and it's in the vector form. So theta I, you have multiple parameters to be estimated. Therefore, you have a subscript I equal to summation of a I n x n. Okay, I is equal to 1 to all the way to p, where the AINs are weighting coefficients. In matrix form, this is theta hat equal to AX, where A is a P by N matrix. In order for theta hat to be unbiased, we require that when you take the expectation, it's equal to the parameter. Okay, so just to put this in a vector form, it will be a more complicated form, but in vector form. Okay, so now let's turn to the next page. The next page. It matches from aspect of theta hat equal to AE x equal to theta. Keep in mind that the linear estimator will be appropriate only for problems in which the unbiased constraint can be satisfied. So we must have that aspect of x equal to h theta. It has to be linear. If the theta model by itself is not linear, then we will not be able to get linear estimator. Okay, so for H is a non-n by P matrix in the scalar parameter case. Aspect of X is something like this. You have S0, S1 all the way, and then theta. So that this is truly the vector parameter generalization. Now we substitute 612 to 611 produce unbiased constraint. So what happens is we want to put this into this. Okay, you put this into this, put this into this. So what? So we have AH theta here, right? AH theta equal to theta. And therefore AH has to be identity. Okay, AH has to be identity. If we define A equal to this, so that theta I is AI x, the unbiased constraint may be rewritten for each A by noting that A is in fact a bunch of vectors combined together. So you get a huge vector A, including every individual column vector A, which represents the coefficient to be calculated. And let Hi denote the ith column of H. So we have this. So with those definitions, the unbiased constraint of 6.13. 6.13, you have A, right? You have A, you have H. So if you imagine you have A like this, and you have H like this, and when you multiply them, they have to be I, then so what happens? First element multiplied by the first element has to be what? Has to be I. The second element multiplied by the second element has to be I. Then how about the first element multiplied by second element? That will be 0. That needs to be 0 because eventually it's identity. So of diagonal elements has to be 0. Okay, so with the definitions, the unbiased constraint of 613 reduces to this. This delta function ij, if this is not familiar, then recall what you have learned in signals and systems. Delta function ij is equal to 1 only if I equal to j. Delta ij equal to 0 if I is not equal to j. OK， 这个 delta function 就是当 I 等于 j 的时候就是1啊。这个是一个讯号语系统里面就已经讲过这个了，这个是很常见的一个人为的定义哦，这是一个人为的定义，这并不是推导出来的哈。人为的定义就是 I 等于 j， delta 就是1 ，I 不等于 j， delta 就是0。OK， so this is artificial, right? So the variance is this, because I think this is trivial. We don't have to repeat that. You have variance of this equal to A, P, C, A, I. Then using the results for the scalar case, the BLUE for vector parameters found by minimizing this, right? You want to minimize the variance subject to constraints like this, because this is actually the constraints of this. This actually represents this. Okay, so you have objective function and you have constraints. So again, this is a typical optimization problem. OK，但是因为我们这门课没有办法讲详细的去讲 optimization 啊，因为这个 optimization 本身是一门也是蛮专门的学问的哈。那也许有的人有修过 optimization 这门课的话，就会比较清楚。没有修过的人，这个 optimization 问题并不是很复杂的。就 optimization 角度来讲，并不是很复杂的，所以你可以看一下 appendix。那这个推导哈，可能要20-30分钟哈，所以可以自己导一次看看。Then the optimization problem is going to give you the solution for this theta hat equal to this h. You see there is a HCH HTCX, and the covariance matrix is this, right? It's always the case that we are interested in two things. The first thing is, what is the estimator? The second thing is, what is the performance of the estimator, right? 这是两件事我们一直在计算的，就是 estimator 先把它导出来，然后再来计算它的 performance。但是 performance 要怎么计算呢？当然就是用它的 variance 来代表嘛。这个既然是 vector version 的 theta， 它的 variance 当然就是一个 covariance matrix 啊。OK， 所以这个是 vector 版本。Okay, so the form of BLU is identical to NVU for the general linear model. Okay, so to make a long story short, if we have x equal to this in a vector form and W is Gaussian noise, then we have theta hat equal to this. And this is the NVU for Gaussian case. Okay. And if the theta are Gaussian, then the BLU is also NVU. Otherwise, we cannot claim this. So now it came to this conclusion for Gaussian Markov theorem. It's actually a brief summary of the previous things we talked about. So if you have a general linear model like this, it has to be linear. And H is a matrix, theta is a parameter to be estimated, and W is the Gaussian vector with zero mean and covariance matrix. I'm sorry, I have to make a correction. W, it may not be Gaussian. It is a noise vector with zero mean and covariance. But the PDF is arbitrary. It can be arbitrary. Then the BLUE is like this, and then the minimum variance is like this, and covariance matrix is like this. So if you take this and take the II element out, it will be the variance for theta I, right? Okay, so I think that would perfectly conclude this session. And there are some signal processing examples. I would recommend you to get a brief reading for that to get familiar with. But some of the examples are actually very complicated because it involves multiple receivers. This is called the array signal processing problem. Array signal processing, 阵列讯号处理的。Okay, so yeah, I think that's we are all good for today, and then we'll continue next day. Okay, thank you.